All right, ladies and gentlemen, it is now 20 past the hour, and here we are for part two of this wonderful lecture. Please, let's listen to Luis now.
Thank you, Maria. So I want to start number two now with lecture number two with what Reinhard just asked. And I want to put it in a somewhat different way. So he was asking whether there was basically, I think he asked sort of the way a physicist would ask if there's a control parameter or an external parameter that allows us to think about what's happening here also in cities. But the way I answered was a little bit different, which has to do with the fact that there's basically controlling quantities that have to do essentially with this sense of density and how it scales with population given the structure of space. And that this forms a certain self-consistency that allows a city to do certain things. That's not quite so satisfying, but that's in the nature of complex systems. And I think in lecture two, you'll see this more clearly. But I want to just bring that back to something that's not so physicsy, and it has to do with the problem that humans and other agents in complex systems face, which is that in some sense, humans are not very different, whether they live in a large city or in a small city, right? There's the same physiology, same genomics, same capabilities. And the same is true even across history. The people that lived, at the beginning of cities 4,000 years ago, 6,000 years ago, were not very different from the people who live today, we think. And so there's this problem of how it is that we create something as crazy and extraordinary as New York City with basically not without changing the nature of people. So this is also, this was my riff on how is it that somebody like Ising could live in Peoria and could live in Hamburg, but it is essentially the same question. And so what I'm trying to show you is essentially how it is that you can create a system that has very different properties from a system that's disconnected, but that uses characteristics that are there in people, but does not fundamentally change them. Okay, so that's kind of the magic of cities, and it is in many ways the magic of development. So this second talk will be about that. Will be about how do we build a statistical picture of what's going on. That's a bit more detailed than what I showed you so far. And this idea that we have to introduce the space of interactions and learning, which becomes sort of a more fundamental space that's not there in simple statistical mechanics. So again, I go back to this. The Ising gave us a new way of thinking across these domains from space and velocities and traditional statistical mechanics that we had 100 years ago when he was doing his work. And now effectively new spaces where we're thinking about intelligence, information, computation, and so on in both artificial now, but also natural environments. And so it amused me when I was preparing this talk that this came out recently. I don't know if you've seen it, NVIDIA is the company that is now the biggest company in the world that creates the chips for AI and gaming and so on. And they just launched Ising, which is essentially a new model, a new AI model to accelerate, turns out, quantum computers, which is a little bit off topic for Ising's original work, but nevertheless, I think this is kind of interesting. And so this emphasizes effectively the connection, if you will, between Ising and worlds that we're considering more from the perspective of computation and information. So, Ising is everywhere indeed, and in places that maybe are or would have been unexpected. Okay, so let's start with this. So I already showed you the slide about principles that establish when it's possible to do statistical mechanics. And I want now, with having shown you a bit of what happens in cities, start asking if some of these things are feasible or not. So effectively, if I think about these various points in the slide and start saying what we have and what we don't have, I could say maybe that we have these. So we certainly have motion. You saw that in the video, you see that in your experience, and this generates statistics. We don't know what the statistics is exactly, but certainly this is true to a large extent. I think it's also fair to say that interactions are local. So I'm thinking about people interacting with each other. Despite what we're doing right now over Zoom, this is also true, and it's a new element. But most of what we think happens in a city is predicated on the fact that most of those interactions, perhaps some of the most important ones, are local. And you still cannot get a good meal or a haircut or maybe even a good scientific discussion, the best one anyway, without it being local, at least in part. And the other aspect, motion is bounded. This is also true. So so far so good. But then part of the problem is that we don't really we don't know what energy functions are for something as complex as people interacting with each other in society. So in this sense, we're not going to have something as simple as things we can write for physical systems. But do remember that Ising's contribution along with Lenz was really to write something new that was not true to the nature of what a magnet actually is, but was an idealization. So this has always been true in statistical mechanics. And so the question for us is a bit of a finer question, whether we can write things that are relevant, particularly on large scales as we average, that gives us the properties of cities and other social systems. So this is still an open question. It depends, but I'll show you some progress in this direction. And so whether we can have this procedure once we have an energy and a probability function based perhaps on that energy and other conserved quantities, if we can effectively compute the volume of phase space or the partition function and get something like thermodynamics. And I'll show you that you can actually, but it's a first pass and there's a lot of work to be done here, but I'll show you some curious things start emerging. Okay, the main dish has to do with the fact that just as I showed you before, there are these two spaces at play. And we need to somehow bring these two spaces together. So there's a space, and there were these two invariants that also show you. There's an invariant that has to do with connections and effectively degree of specialization in the space of skills, if you will. And there's another space, which is motion in space and time and velocities, right? So the space-time part is external to individuals. It's something that we can do to particles. That's the basis of statistical mechanics. And so it's conventional. We know what to do. But the space of skills and interactions is in some sense new, and it's unconventional, and we have to be able to deal with it in some way. So this is basically what the novelty is and how this space connects with the other space that endows it with certain costs and benefits. Okay, so this is what I call in some of our papers a social reactor. Essentially, a city, if you will, is a place that it's bringing people to interact together, a bit like a star. When people interact, social products emerge, and these social products accelerate with degree of interaction, and that's effectively the small to large city effect. It's kind of a scaling of what happens then. But the reason why all this happens is really to do with the space in green, the skills and interactions. And so we need to basically anchor that there. Okay, what I'm going to use to square the circle to make sense of some of this is essentially that this concept that's demonstrated here schematically of what geographers came to call life paths. A life path is essentially your spatial trajectory. Imagine it in a day, right? So you start at home, you go maybe have breakfast somewhere, you go to work, you spend some time, see some friends, go to the grocery store, come back home. If you have kids, you have to do that and so on. And so it's a space-time trajectory that's usually where you move between places, where we have interactions, and you tend to return home. So it's some sort of closed path that changes with variations. And this creates essentially, the interaction between these life paths, or for a physicist, world lines, create essentially a statistics, a dynamical localized density map. I have some animations of that, but in the interest of time, I'm not going to show you. And also start characterizing the kind of velocities that you have between places and how much they can vary. So the physical part of what happens in a city can, to a large extent, be described in terms of positions and momenta. And that's what I'm going to do in the next few slides, and then I'll come back to that space of skills. Okay, so the procedure is going to be that even though the motion is very variable, driven, and dependent on decisions, we're going to have these essentially four variables. An agent performs a closed path, which is sort of this daily cycle, a life path. The path is a sequence of trips, and each one of these trips is characterized by variations in momentum. So it's just basically you move, and then you stop, and then you move, and then you stop, and there'll be so many of these, will be proportional. These episodes, there'll be a number of episodes proportional to the number of interactions. At each location, then you may interact with other people. and exchange things. So, for example, exchange money or exchange information or exchange goods and services or whatnot. And as you do so, this basically means that you can change your internal space to have better interactions. And this basically changes the space that I'm going to be calling G in analogy, but not exact correspondence to what I was calling G before in terms of the valence of the interaction when we did part one. So there's also an approximate energy balance in which you get an income from these social interactions. You have some expense from the other social interactions that go in the opposite directions, and you have mobility costs. And if you want to single out, you could also single out housing costs, but I'm not going to do that. So this is what economists do. This is called a budget condition. But for a physicist, it's basically a conservation of energy per unit time, which once integrated over the cycle is a conservation of energy. Okay, so this is basically setting up something quite simple that has in part a conventional part in positions and momenta, but has also a new part in interactions and skills. Okay, let's look then first at space-time, which is easier. And so the point here is that instead of doing something very conventional that's totally local in time and then averaged over some indefinite time, we need to do something that's a little bit coarse-grained to this life path over the cycle. Okay, so this daily cycle becomes the basis for statistics. Okay, so if I'm going to write something like position and momentum, I'm going to write something very conventional. All right, so what I'm going to do is write basic Newton's equations of motions for position as momentum, some momentum, some mass. Maybe if you drive an SUV, you have a large mass, but nevertheless, there's something that accounts for dimensions. So I'm just keeping physical dimensions. And then this momentum may have a conservative force, but most importantly, has some dissipative force, which is this cost that we already computed on the average, the cost of dissipation over the network. And there's a driving force. This driving force is what's a little bit mysterious. We're not going to say a lot about it for now, but it's basically the force that impels you to go and have that cup of coffee or talk to your colleagues or come back home, right? So it's basically a force that takes you from place to place and allows these interactions. But from the point of view of statistics, we actually don't care too much about why the force is doing that. We just have to quantify what shifts in momentum it creates and try to therefore get at the statistics that it creates. So that's the trick of statistical mechanics, is that we can forget about a bunch of things and just concentrate on a few aspects of the force. So, in terms, for example, conventional models of conductivity and so on that I used in part one, is essentially a Drude model where the force is driving the momentum. Okay, so but all the complexity of this is hidden in the dissipation, which has to do with the network and so on, and this driving force, which has to do with desirable locations and social interactions. Okay, but if you allow me to go on, I can write an energy function, just still the conventional energy function, and which is made out of kinetic energy and some potential energy, and I can take its derivative. And then what I find using the equations I used before is that I have a dissipative part. So I'm just using the equations of motion. You've done this before, I'm sure. Take derivative, put the p dot and the x dot back in. So here's the x dot, here's the p dot, forms the kinetic energy. So basically the dissipation is proportional to the kinetic energy with the damping coefficient and is proportional to F times P. And once I integrate this over time, so this circle integral is basically over the path. Oops, sorry. This gives me the difference in energy over the path, which this is still only the spatial part. And basically, this is the dissipated kinetic energy and the work done by the force. So this is Fp dt, because I'm integrating in time, but you can see that I can trade this for an Fdx, which is the definition of work. So this is the work done by the force. So you can think about your motion through space as some force, the force that you walking or the force of your car or whatever you use is doing to move you through that space. And this induces some dissipation. So this is inevitable and hides a lot of detail, but allows us to do something simple. So now I can say if basically at the end of the day, the force compensates for the dissipation, which in some sense must happen because you get home, then you don't run out of gas or energy, hopefully. Then what you get is that the average kinetic energy over the cycle, over the t circle, which is the time that it takes to complete the cycle, is typically 1 day. then is basically the work done by the force divided by this, which is dimensionless. And so basically this energy suggests that we could probably start defining a temperature. And this temperature is the temperature of your motion, right? And because we tend to work in 2 dimensions in cities, this is just proportional to the temperature. So this is kind of cute, right? It's very simple. I wrote about this a long time ago, but it's just starting to say that you could interpret physical motion of people in terms of a social temperature of sorts, right? So this is just using the math of statistical mechanics a little bit recklessly, but allows you to do the direct analogy of what we usually do. Okay, but let's do this a little bit more microscopically and actually think, because when you do statistical mechanics, remember what we're really interested in is not in averages of straight up quantities like x and p, but on their variance, basically on their variation, right? Which is usually a variance. So basically, if you think that the trajectory is a bunch of mobility episodes, which I have these humps here in the positive direction and negative direction, and these have some average momentum over the episode, and then some spaces in between, which are when you're interacting with people, which you're not characterizing just yet. Then you have a bunch of these bumps, a bunch of impulses, positive and negative, that make up the day. And each one of these, the number of such bumps is basically the number of interactions, which I'll call K, in analogy to what we did before. So, which is usually just proportional to the density of interactions. So in mean field, it's just N over AN. But I'll just keep it as K. And then at each one of these, there's basically a variation of momentum, right? So it goes up and goes down, but there's basically a certain variation, right? So that's what we want. We both basically want to ask, what's the variance? And the variance, the number is basically sum, K sum, over a number of episodes. And so it's proportional to K. This is what's important. So the sum of variance of each subtrip, I'm assuming they're independent in the sense that, you have energy to perform each one of them more or less the same way with variation, is basically the sum of variances. And so this variance is just, and so the idea also is that the amount of energy used per trip is more or less is a statistical quantity, but it's not scaling with n. It's just basically something that is a constant in n. So with these, we basically get that this kinetic energy that you end up dissipating is actually a sum over episodes of an energy per episode. And I can write this back in terms of the quantities that I used before in terms of the dissipation per person, which we derived in lecture 1. If I put a K there, I have to put a K0 here, or I can write it in terms of the variance. But basically this says that the average energy per interaction is the same number. I shouldn't say conserved here because it's being dissipated, but it's the same number. And there's a number of episodes, which has to do with the number of interactions. So again, to Reinhardt's question at the end of my talk, the number of interactions is what's doing the work. Okay, and if I use that, again, back to the machinery of statistical mechanics, I can form a probability, maybe Gaussian, doesn't really matter, but then I compute the volume of phase space. I have n people. In general, I would have some variation here and I have a geometric mean, as I mentioned here, but if you allow me to do this basically in mean field, I basically get this quantity, which is basically the energy dissipated per person, which is times Kn, but this would increase with n. So basically this increases with Kn. Okay, so I can write an entropy just using Boltzmann. This is like in the microcanonical because the energy is given at the moment by assumption. So I can write the number of states basically as n, d over 2. D again is naturally 2, so I can almost forget about that. And there's a logarithm of this kinetic energy. So what I did is conventional, is just having a way to compute what this kinetic energy might be. And I said it's a series of episodes between interactions. So this increases in general because K increases with n, but let's hold on and let's compute other parts. Okay, so this means that as you get more episodes, your momentum increases more and there's more entropic space to explore. Okay, but what about what happens with space? So with space, we saw essentially that there's less space per person. And so I'm going to assume, without deriving the statistics the same way as I did, because it's a little bit more complicated and depends on a few assumptions, that I can write this in terms of an over n, which before I wrote as a0. It's just independent, sorry, so this is not quite right the way it's written, but it's a 0n to the minus delta. But anyway, when I write this down, I end up with something like this, which, as I said, is decreasing. And so when I put all this together, I get a factor of n to the minus, forgive me, this is delta, not gamma. So this is n to the minus gamma, n to the gamma, uh, sorry, delta, but they cancel basically because this is decreasing and the other one is increasing. And I get just the entropy just goes like the log of this G. So this is rederiving what we had done basically heuristically. It's telling you that the volume of space times the volume of effectively momentum space essentially compensate for each other. And under the limits and approximations I showed you, basically this product is invariant, which I show you empirically with the quantities I have at my disposal is true. So the entropy increases with the number of people, therefore degrees of freedom, but the entropy per person in these two spaces, which are these conjugate spaces, essentially is maintained. So this is the mathematical expression of people not having to change fundamentally, because remember that there's a certain fundamental space and there's a certain variation of momentum, but these get scaled up in larger cities, but these scalings effectively compensate each other and preserve essentially this entropy per person, the specific entropy. Okay. And just for fun, since I have this, I'm going to also do thermodynamics, right? So I'm going to define a temperature, let's call it a social temperature, and a social pressure, if you will. It's again still in space. And I define these, as in the microcanonical ensemble, as derivatives of the entropy, right? Relative to energy and to volume, which is the area of the network. Okay? So when I do that, here's a way to rewrite the entropy in terms of a total energy. Remember, it's total energy I have to take derivative of. And so I write total energy like this. And so what I get is essentially that this temperature now goes like the dissipated energy prefactor n to the delta. So the temperature is increasing with city size and therefore effectively with interactions. And the pressure, I go through the math, here it is. It's basically just goes like this. And so I got a little like equation of state, which is reminiscent of ideal gases. It's basically the number of particles times the temperature. I have K Boltzmann is equal to 1 here. And then there's a pressure times the area of the network. And so I can write something that the pressure, basically taking the area of the network back there, is given in terms of these constants that I measured before, n to the 2 delta. And the 2 delta is because these two effects compound in the pressure. There's both more energy in terms of temperature scaling up with population, but there's also less space. So the pressure is bigger because these two effects basically multiply each other and give you a factor of 2. Okay, so that's kind of beginning of a thermodynamics. I assume certain simple things to do the calculation, as you've seen, but this allows us to start making a bridge. So if you ask, what's this pressure? Well, it shows up in a bunch of things. We never thought about it until recently as starting to measure it. But a few years ago, we had these papers on building heights and values of buildings. These are single family homes. And so it expresses itself both in terms of magnitude of costs per unit area, per unit space. So there's more money per person in larger cities, but there's also less space. So these quantities compound these two effects. And you see, for example, there's a slope here for houses that do not change their height, but these are single family homes, but that you measure their value basically goes like 2 delta. So this is a proxy for pressure, but it shows you can start thinking about the pressure that you see basically in a city as either the price or the height, if the price is maintained per unit, of various buildings. And so you start seeing the city essentially as a landscape that's reflecting some of this. This is a bit, pushing what I just showed you, but I think has a grain of truth, and we're working to better interpret this. Okay, so let me just go to the skills and interaction space, which is more interesting, and just show you what may be happening there. And then we have about 20 minutes maybe, and then try to conclude and come back to both Zipf's laws and so on, and why they may be maintained, but also a little bit to Ising. Okay, So in order to do this, I basically have to go back a few steps and start talking about how the Ising model became more than what it was meant to be, which is a model of magnets, but became actually a model, the first model, and in some sense, again, the simplest model for statistical learning, for basically what we now call machine learning, but also for models that exist in the brain. Okay, and sort of there are several precursors, but the clear contribution was John Hopfield in 1982, so a while ago. They basically wrote this paper in PNAS, and just a couple of years ago won the Nobel Prize in Physics for this, for having established some of the foundations for machine learning as statistical mechanics. Okay, so this analogy is also interestingly mathematical, but it relies on a couple of twists, and we're going to use these twists a little bit in spirit, but you'll see in a moment how they work for us. But basically what Hopfield did was to write, so here's the Ising model, as Ising and Pauli and so on, as we've heard, wrote it. And here's what Hopfield wrote. So basically it's the same thing. It just replaced the usual coupling J by something called W, which is W became conventional for connections in neural networks. And so what we did then was to say that these were not just fixed numbers, but basically the structure ij here is essentially just fixed number of the nearest neighbors, typically in Ising, and then you can generalize. But what he wrote was something that's still local, but that looks like this. So the idea is that there are patterns. So these are basically ways in which data is combined, and these are best described visually. I'll show you in a moment what this means. But there's something which are basically data, things that are patterns in data. And I can write the interaction term in the Ising model in this way, in terms of these patterns. So again, there's a typo here. This p here is a mu, so it's basically summing over p patterns. Okay, but that's basically I and j. So these are some localization of the pattern in the lattice. Okay, so what happened here is that it's no longer a spatial lattice; it's a network. This is very, very, very important, because now each spin can be connected to any other spin, much like in a city, anyone can be connected in principle to anyone else. So this shift from a spatial lattice to a general network is fundamental. And this sense that the connections are not just sitting there, but actually are representing things is the other big, simple, but big sort of departure. So if I do this, I can basically write the energy of the Ising model in this way. And you see here that basically the energy is minimized by S's that align with the patterns. You can see this by basically recognizing that this is an internal product between the Xi and the S, right? So basically what happens is that the Ising model, which was about magnets and describing the Curie point, now becomes an associative memory. You can remember patterns that you put there. Okay, so it becomes a place in which you can encode and decode patterns from. Okay, and so, and more, if I want to basically, if I didn't know what this W was, but I want to learn it, so this is where learning and inference comes in. I want to know what it should be in order to remember patterns. What I do is to use the same model and put the S's to the patterns, as you can see here, and then ask what W should be to minimize this energy. And when I do that, basically, I get that I should update the W to be this, because again, you see that this will minimize the energy. And so the W ends up being the sum of the patterns with some weights for how likely the patterns are. If the patterns are equally likely, which was assumed in the previous slide, then it's just basically the W that I showed you before. So this is super simple, but has these twists that make all the difference, right? And so just to show you how this works, you probably have seen, but this is for digits. You can put this on a lattice. So basically you see here on the bottom, there's a query. So basically you want to know if the number is 0, you give it a noisy pattern, and then the network, by basically converging this spin model to the minimum of energy, recovers the pattern, right? So you see it there, a noisy pattern, and it recovers it again. So it's an associative memory that can denoise, that can basically recover a pattern. Okay, so this is the beginning of one of the beginnings of machine learning because it allows us to start to see how information, not just randomness, can be encoded in statistical mechanical systems and in particular to the Ising model. So let's just talk about the city then. How can we bring this to the city? So I already told you effectively that in a city, in interaction with others, we basically start encoding certain spaces that are useful to others and not useful to us in interaction. And that is a learning and adaptation problem in a social network. So it is a little bit like what I started to tell you about the Ising model used as an associative memory. Okay, before I get into the math, I just wanted to give you these two quotes, which are well known, but so the first one is from Matt Ridley's book. He writes a lot about evolution and learning and development. And there are many quotes in the spirit, but I like this one that because it's about people. So even those that have several paying jobs have only 2 or 3 occupations at most. So this is actually trying to make sense of what I was showing before as data. But they consume hundreds, thousands of things, right? So if you think about all the things that we consume and all the people that touch them, this is the very thing that also Adam Smith had realized. They're incredibly diverse, whereas what we end up doing is actually quite specific. So he mentions that this is a diagnostic feature, the main feature of modern life, the very definition of high standards of living. We have diverse consumption, but simplified and specialized production. Do one thing, but use lots. So again, this narrowing of our individual functions and widening of our connections to obtain things, okay? The effect I was showing you before. And of course, this is well known. It's often called Adam Smith's theorem. It's not a theorem. He didn't prove it, didn't do math. But this idea that specialization is proportional to the extent of the market. Okay. And for us, this won't be a market explicitly. It will be a network. Okay. So what's happening? So let's think in analogy to the Ising model as an associative memory that there's a certain demand out there. And this demand is basically created mostly by other people in your social network, by people in the city, right? So there may be people for us that are looking for education or they're looking for information. And so there's a pattern out there that you need to match. And each person has, at this moment, some representation, something that matches that pattern. And the idea to do the math is that these two pattern and representation things live in the same space, much like a space of spins and the space of patterns live in the same space. So how shall an individual satisfy its demand? So there are 2 ways, right? Going back to the ideas we described, you can do it yourself. So you have your own representation, your own production, and you match your demand, and there's some interaction term, which in this case could be almost zeroed out, but just to say it. And you can do this so that's autarky, an individual alone, or basically people who are self-sufficient, or you can do it via interaction. So you basically can rely on a sum over people, neighbors, but these are basically people in a social network that produce their own thing. So you rely on the production, on the skills of others. Okay, so this is society. So as you can see, even though I'm writing them here as differences and before we're writing them as internal products, basically if you take the square and ask for minimizing this, it's the overlap between the G and the D that gives us effectively the match, right? So that minimize an energy that would be built on these differences. So what happens is that effectively, as you go across your life path, you come up with some demand, you're hungry, you go for breakfast, or maybe you make your own breakfast. That's the idea here. And then basically you have the next interaction, maybe at work. So there's a series of interactions, a bit like presenting the data one at a time and adapting one at a time. And each one of these, I'm going to assume, and you'll see why, that there are also costs of learning, which are basically having to do with switching on the interaction, switching it off. So it's a bit like the episodes of travel, but these are more internal and probably consume less energy. But I'm going to use this as, if you will, a regulator of this dynamics that I can then take to zero almost, but it's good to have because it lives over the same space. So again, this happens a certain K number of times. And in probability, when I do this, what happens is that I'm basically creating a probability, a posterior of what my internal representation is as I go through the sequence of interactions, basically with the demands and the skills of others. So this becomes essentially a product of, if I assume that each one of these episodes is effectively independent, or there's a factoring, just for simplicity, is essentially there's basically a product of likelihood functions which characterize how my skills interact with the demand and the skills of others. And so this happens basically the number of interaction times. So this is essentially Bayes' theorem. I start in a certain state, I end up in a new state that's given by my interactions. And this is inference and learning, because my final state is going to be different and is going to be informed by the characteristics of others. Okay, so the math of this, I don't know if you've done inference, you know exactly what I'm doing in this slide. If not, it may be a little bit too much for the time we have. But the idea is that there's an energy. You can think about it individually, or you can think about it now in society with a sum over neighbors. And then for the whole network, you sum over these energies of individuals, and you can build a probability out of this, which is basically how G is changing given the demand. I change notation here, but basically the demand and G of everybody else. And there are two situations. So you can ask basically, what is the statistics of the G's that follows from this model? So if in autarky, when you're alone, your G just follows from your own demand. There's some normalization having to do with the K's, but it's basically dictated by your own demand. You do what you need to survive, right? You're dedicated to survival functions. And the variance is basically given by, if I put a beta here, it's just some parameter that controls for that and the magnitude of this K. But basically is of order 1, or is something that has to do, sorry, not of order 1, but having to do with the basic space of variation between the space you need to cover of your own needs, right? Let's call it D0, which is the number we used when we're looking at professions. So this is basically the baseline. So in society, what happens is that something interesting happens. When you combine all this, and you have to see that when you sum over the EIs, there are cases in which others are satisfying your needs, but also there's the reciprocal in EJ, where you are the one providing something for the demand of J. So you have to group all these terms together, and you get something like this, that your G, your basically space of skills, is now a sum of interactions, but it's basically given by the residual demand, the demand of others that's not taken by everybody else. So this is why you need to specialize, because if the space that you're trying to cover is being taken by other people, then in some sense you have no G. The G becomes very small, and by extension, essentially your income is low. But on the other hand, to the extent that this G is useful to others, you have a lot of interactions and presumably a better income. So this is why what is interesting about these models is that individuals become specialists. But then even more interesting is that this variance basically shrinks by the number of interactions. So this sum is basically a sum over J, which is the number of neighbors, which is the number of interactions, which is K. And so basically the variance now becomes concentrated on these spaces where you have effectively comparative advantages. What I showed you is a story about people, but basically it's inference. What I've done is just basically how to infer the average of a Gaussian as you give it data, and how the variance shrinks as you do that. So the number of instances here is the number of interactions, which we're saying scales like n to the delta. So specialization is proportional to the extent of the network. And the extent of the network, as we've seen, is proportional to the size of, not proportional, but scales with the size of the city. Okay, so I'm almost sort of to the end of the math, but I can put all this together. I'm going to do it a little bit faster, but I'm going to say that this space of skills has some dimension that I don't need to specify, but it's not spatial. So I'm going to call it DG. Maybe this is a simple number, but I'm just going to leave it there as a placeholder. And I have these two variances that I need to have a space of G, and there's a space of the momentum of G, which again is a series of episodes as before. And so I'm going to call this WG as a baseline and D0. Remember that now what happens is that the n to the delta and to the minus delta factors cancel. So again, This is a space where I have more connections, but also less internal space because I'm specializing. And so the entropy that is related to this internal space is basically something that, I'm sorry, I called it A here, but it's basically this space, this product here. But it's basically, I think I called it GS in the slide before. Here's GS, see? So basically, when I put it all together, the space out there of mobility and momentum, and the space that's internal of skills and special and interactions, I get something that has only a factor of n in front, but it's made out of these invariants. So there's basically an adiabatic invariant that is basically related to the fundamental characteristics of people. Remember that these is the space you need to cover in your essential needs. And this is the dissipation of basically each connection that you interact with others. So these are characteristics of individuals no matter where they are. And as we saw before, also the dissipation and space per person have some of these characteristics that are individual, not collective. And so you end up basically with an entropy per person that's invariant, but then a factor that multiplies this over the entire system. So what this says is that there's also an interaction, specialization, temperature and pressure. I'm not going to derive it. They have some of the same scalings. But this means that the entropy per person in a large city or in a small city is effectively the same. So there's no net flow between one space and the other space, at least as predicted by this treatment that I'm showing you today. There are exceptions. For example, international migrants tend to go to large cities. People that are young with education tend to go to large cities, and vice versa. People that are older, have less education, tend to come to smaller places. But this are basically life cycle and other things that start shedding light on how this breaks, but that also start to show you when the invariance can hold. Okay. So that was more or less the statistical mechanics, and I hope that this encourages you to start thinking about how simple models of physics can capture some basic things that are fundamental about how cities are organized, and even how we're organized vis-a-vis each other. And that allows us to start thinking about how cities of all sizes can happen, and how a person can live in small cities and big cities and be the same person and have a happy life maybe in both, though with different specific characteristics. So this provides a simple statistical model for urban scaling in cities, but does not really explain the growth instability. So I'm not going to explain it because this is in some sense the mother of all problems, but I want to come back to that and just say a couple of things. Okay, so over the cycle, basically there's essentially a total supply of I. So this is what I gets. It gets basically the supply from others that satisfies its demand. And I creates a certain supply that satisfies, which is basically just proportional to its connectivity, total connectivity, times its own space of skills, okay? So we can write an energy balance equation that just brings these things together. And the social interactions where you have an income, where you have social expenditures, economists like to call this consumption, and then you have transportation costs. Again, you can extract out the costs, but this is the way we wrote it. And we could put in even here also the cost of interaction, which is effectively a kinetic theory of switching these degrees of freedom. And what happens when you have economic growth is that basically this grows exponentially. But it grows exponentially with a very small fluctuating number. So we assumed before that this was zero. And it is zero approximately in the short term, but it's not zero over decades. It becomes a large number because this will grow exponentially. When you look at this magnitude of this number, I just put a number here. If you use 3.65, you see why doing this per year. This is a percent of GDP growth, for example. There will be strong GDP growth for most nations. But this is just 0.10 to the minus 4 per cycle, per day. Okay, so what people experience as they go through this dynamics is very, very, very small growth, if there's growth at all. So what must be happening somehow is that there's a very small accumulation that tells over the long term, but that in the short term is small. And this has interesting characteristics. It means basically that income is growing faster than the other activities. And so there's a net. And so this requires effectively that this learning has a temporal component, not just a city size component, but it gets expressed throughout the system. So learning improves with scale. It accelerates production, as I said at the end of the previous talk. And this also accelerates gross in consumption just for economic growth, but for other quantities, other accelerations will beget. So why the number is this number is kind of a great challenge that we don't know how to compute yet. But you see that you have the mechanics to start doing it. Okay, so this is more or less my last few slides. We started with this idea of effectively a lot of early statistics coming from the social science into physics. And I propose this alternative title to Philip Paul's paper in terms of the social modeling of physics. And I think essentially that's what, in part, I've dedicated a lot of my career to, as you can see. But what this does, as you can see, is that it's not only about society, it's also about physics. It's about what we do with statistical mechanics and the fact that increasingly statistical mechanics has to incorporate things like learning, networks, and computational costs, which is what I showed you can do, though it should be done always better, for cities. But similar ideas can be applied to other networks, as you might start to imagine. So these have been missing ingredients in traditional StatMech, and they're in some sense the state of the art, whether one is doing machine learning models or cities or innovation systems, as we start to understand these systems from a more quantitative, but also a more statistical approach than has been possible in the traditional social sciences. Okay, so I want to end basically with this slide, which is a big summary of where I started, that in some sense, physics, and statistical mechanics in particular, was early on about matter and energy. This was even true, of course, to a large extent about the work of Ising, and it's best expressed, of course, by Einstein's work and the equivalence, which is formal, between energy and matter through E equals mc squared. And so in this sense, physics, at least 100 years ago, was a discipline about energy and matter, not about information. Information was denied because we worked in maximum entropy. But ever since, many things have happened, right? So we understood better how effectively entropy and statistical mechanics is put together. And so this is partly the work of Ising, giving us an essential tool to think about this. But then we also started understanding how information is physical, so it pays costs, and how it is information in terms of this work about instability, that it is information when it's encoded in systems, particularly in people and networks of people, that it creates growth. It creates a change in time. And at the same time, we've also come to understand communication and computation through information theory and other methods. What is missing, but I hope I give you a little bit of hope, becomes possible in something as complex as a city, is a synthesis of this into something that we call complex systems. But in a way that is not opposite to statistical mechanics, as you saw Kadanoff was starting to do, but in fact is a better statistical mechanics and honors sort of the tradition in which Ising was working at the beginning of his life, and also helps explain how a life is possible in either a large city or a small place. So that's it. Thank you very much.
Maria, microphone, please.
Oh, sorry. Sorry about that. So again, let us thank the speaker. I see lots of applauses. Very nice. I would do it too, but I just don't know how. So let's open the floor for questions. And if there's any questions, please, let's see. I don't see any hands raised. So let me ask you a very, very dumb question, which is, right, you showed us a lot of beautiful scaling laws, even in systems that, one was not, that I wouldn't think naturally of seeking a scaling law. But are there any systems that these scaling laws do not emerge? Like, is there anything that cannot be explained in this way? And also along these same lines, like, the same city or the same, like, how do things like, let's say, the political system change these scaling laws, or the weather of the place, or the something that, because do all cities follow all the same stuff, or are there some kinds of characteristics that differentiate them?
No, for sure. So this is the magic of scaling, but also, if I may, the magic of statistical mechanics. We know the Ising model is not a good model of an actual material of a magnet, right? But on large scales, it's a very good model in the appropriate dimension of the Curie point and so on, right? So yes, there's a lot of I took this talk as a talk I was giving to physicists mostly at Yuri's advice. But yes, absolutely. If I was giving this talk to social scientists, I would have given a very different talk emphasizing how every person is different, how every city has a history and it's quite different. In my job, I'm a professor of also evolution, ecology and evolution. So biologists also have these concerns. So in some sense, there's an historical process that and a process that naturally creates difference and diversity and contingency that's also there. But this process, what is magical and what was not known is that this process coexists with a lot of these statistical averaging that you find in scaling laws. Okay, so having said that, to answer your question more narrowly, there are a couple things that can be said. First, what I showed you in scaling laws is that there's always some scatter, right? So they're not perfect. And I showed you, for example, if you remember, the one for crime has more scatter. So there are quantities that are more granular or more specific that don't scale so well. So as you chip away at more precise things, so for example, people try, because scaling is so simple as an XY plot, you can do it to anything, right? And people have done it. So if you start asking questions about hospitals or airports, to the number of airports scaled cities, that's kind of silly because at some point you don't have an airport, right? And so it breaks down, right? So if you ask it finally, scaling doesn't work, or at least breaks down at some point. But what I was showing you is actually quite aggregate quantities. The GDP of a city, which is basically everyone's consumption or production, or the infrastructure of a city, which is all the roads. So it works best for those quantities. They're actually quite aggregate. So scaling always is a big average. But even then, you find these fluctuations. These fluctuations are not fluctuations as in physics. I said this in passing, but they reflect the history of a city and so on. So Silicon Valley always was rich. Some cities in other parts of the US, particularly in the South, have been poor, so they stay below the scaling law. So you see some of these things, but as you disaggregate, then you find people again, and you find places that are very specific and so on. The magic is that it seems that as you aggregate, you have a logic for how these things work. That's truer to what we can do with statistical mechanics, which was my goal today, was to show you that. But yes, everything breaks down as you go down. But that's not to say that that's a better truth, right? It is true that you should respect every person for who they are, but it's also interesting, I think, and I'm taking my defense here among statistical physicists. It's interesting that there is a collective behavior that creates these great advantages of productivity, but also a certain claustrophobia, right? And that creates that it sets in motion a dynamics of collective learning that leads to development and so on. So that's not visible in each person, right? You'd have to really look for it, and you would be confused if you look at the individual level. So I think what's magical here is to be able to go across scales and be able to see there are things that emerge on large scales, scaling among other things, but there's a respect, particularly with people, for what each person's doing and how they're different. And in fact, the statistical mechanics tells you, curiously enough, that people should be different, right? I just showed you that. Because once you include learning and information, we are in some sense the niche that's created around us by all the people we interact with, which we choose in part.
Okay, thank you. I see there's two more questions. So one is from Tuan. So let's hear it from Tuan.
Thank you for the great talk. And you said it's magically happen on this scaling and very beautiful. But I have a question because of my naiveness on that question, so on and so forth. So for instance, you make the connection between the socio-economic scaling with the whole field model and the Ising model at the end of the day. But the Ising model or the whole field model, like associated memory in general, you optimize for some global cost function, right? So the energy
right.
function, or in classical statistical physics, you optimize for the free energy, and the free energy also a global function. but then in society you have agent, and then because of social interaction, right? It seems like it's a very decentralized system. So you don't have a common objective function, a global function to optimize, but everyone optimize for his own utilities. So it seemed to me a very magical that so two different type of optimality, right? Optimality for global function and optimality for the local utility somehow both show up some kind of scaling behavior. And in connection to statistical physics, like Kardanov scaling or even hyperscaling, it requires the system to be close to the critical point, right? But in the context of a social economic system that you show, it does not seem to need to be in any vicinity of the critical point. So can you just elaborate on why this kind of optimality for local utility function produce similar like large scale behavior as optimality for global function?
Yeah, thank you. Your question is very insightful, but there's a lot in your question. So let me try to take you one at a time. Yes, so just let me start with a comparison with the Hopfield network and the Ising model. Obviously, I used that as a jumping board. It's not exactly the same what I ended up doing. I used more like a diffusion model or an energy model when I jumped to society, if you're familiar with those models, rather than associative memory, like a Hopfield network. But there's a similar logic, right? That the patterns are basically matching and so on. So just to say that technically, but the point is, in the city. So I think there's something interesting in your first observation, very interesting in your first observation that has been in my mind, but I haven't resolved. But I think this is my attempt at an answer. I think in a city, and in fact in most complex systems, the pattern cannot be global, right? Like in a city, you cannot interact with everybody, or in society, you cannot interact with everybody. So you have, in some sense, a certain subset, which is a heterogeneous subset that has to do with your motion and who you can visit and a bit of your history, which basically gives you a more local optimization. It's not totally local, but it's more local. And this is in part set by the first part, which is the mobility and so on, which is limited by energy, but also other things. So I think actually that some of the things that people have not done in machine learning models is that they've not taken in some of the physical constraints of systems to become more local, so not be global at least. And because of that, you end up with global optimization. That in some sense is not great. It's good early, but then the system freezes, right? It cannot do more. Whereas with local but increasing neighborhoods, which is essentially what's happening in the city, you have local but scaling up connectivity patterns. You can learn more, and you're never done, and you have a system that stays fluid, that stays learning. And you can also put in new pieces and take some pieces away, and the system adapts, right? Because again, it's a local adaptation, and it focuses on these local memories that are associated with each individual. So I think that's what's special about the city. And I think but at the same time, this touches this very important problem, even in machine learning, which is the fact that learning, even in the big model, seems to freeze, or not freeze, but slow down, because it's global. So that's an interesting point that's been underexplored, but it's a place where complex systems may be able to inform machine learning models of why the learning should not be totally global. Then the second part of your question is a little bit trickier, and I think this has to do with a different nature of criticality in complex systems versus more traditional physical systems. So in physical systems, usually one is looking at something that's stationary, and one is looking at the nature of correlations versus some parameter like temperature or something. Whereas here, actually, what's happening is that I spoke about a phase transition that I didn't specify between a connected system and a disconnected system. But once you're in the connected system, the cities, then you basically have that you can almost achieve any scale as long as the assumptions hold. And that system has dynamics. It's also a system, I didn't emphasize that except at the end of each talk today, but that system has a different character. It has a certain self-similarity that is different. So in some sense, you already are in a phase that has a certain self-similarity, but it's not like a critical point in conventional statistical physics. And so I think that is something that we haven't really clarified in complex systems. It's a point at which there's still a lot of confusion, because we often in complex systems see scaling and we think, it must be a critical point, because that's why we have them in the traditional models. But I think hopefully what I started to show you today and the work shows is that these systems have a somewhat different character that allows them to scale without necessarily being a traditional critical point. But that in some sense they are a critical point, but they're a different kind of thing. They can exist at all these scales because the energy is not fixed, for example. It's coming in on demand. So that's what gives them dynamics too. But in both points, I want to emphasize that your questions are very insightful, and these at the extreme are open questions. But I think in doing this work, what I want to show you is that we can reason through these very complicated questions in a way that's more principled and even make contact with traditional models, but then take them to new places.
I just want to point out there's a little comment by Yuri that says this is more similar to self-organized criticality.
Yes, obviously it's self-organized criticality, but it's one that starts bringing in, it's a self-organized criticality period, but it's not a sandpile, right? It's kind of like this whole system that's also learning and doing a bunch of new things. And I think this connection to learning and the fact that this learning, the way I showed you, is also self-consistent with the demands that people are bringing to the city. So it's kind of almost endogenous. That aspect, I think, is quite new and has more to do with cities. And so that the self-organized criticality works partly through the space of information is new relative to the old self-organized criticality models. And I think this is where we're trying to go with statistical mechanics, including the connection to machine learning. Two-to ones. So this is kind of very exciting, to me anyway, and I hope to you.
Indeed. One more question from Reynard.
Yeah, well, I hope it's not a trivial question, but you look at cities, and then I came to the idea, what about countries? So a country has a lot of cities. What can you say about the rest? What is this? And could you have a hierarchy to characterize a country like you characterized the cities in different way? So therefore, is there a possibility to apply those scaling laws, at least in part, to different countries?
Yes. So of course we tried, and many people have tried. It doesn't work very well. So it seems that so this is why cities are kind of interesting. They seem to be a more organic, if I can use that term loosely, social unit. We think because of the structure of connectivity, a city even in statistics is basically defined by various senses as a network of people who live and work in interacting with each other. And the country is not that, it's more loosely connected. And in part is an urban system. It's a collection of cities, big and small. But effectively, the reason why and across cities, as I showed you briefly when I showed you that plot across time, the baseline is shared. So the baseline is basically the GDP per person, and then which is bigger in larger cities and small in small cities. But basically, there's an extrapolation to the individual, which is shared. And when you look at countries, this is not true. So for example, if you think of the largest countries in the world, they're China and India, right? More or less the same population size if you go by population. And what you find is that until recently, they used to be quite poor. So for example, if you did scaling your GDP with population, whereas smaller countries like European countries and so on are small and rich. So if you start counting the fact that they're urbanized, it helps you a lot. Because then the urbanized countries are much richer. So urbanization is actually sort of a state variable that helps you. But the relationship is not a simple power law. So there are things like this that you can build from cities because now you can aggregate over cities, right? If they're scaling at city level, you can think of a country as a collection of cities and settlements. But it doesn't quite give you a clean scaling law at the national level. And in fact, it seems that cities interact with other cities and places across countries more easily and form these urban systems that have to do with free flow of people and other things. So it could be that just like Europe before the 17th century, that maybe a world of cities makes more sense than the world of nations. But nations seem to be fairly artificial. Nations have a lot of properties that are not good, well described by size. Any size.
That's actually very interesting to hear. Any more questions? Well, if there's nothing else, no more comments, no more questions, let's thank Luís again, and also thank all the speakers of this session and all of you that attended until the very end. Thank you all very much.
Thank you. It's been a pleasure.